Okay, we will start now then. Let me close the door to not disturb all the people who are probably not even here today on this floor. That's fine. So last time we talked about the Jacobian and derivatives in for functions from Rn to Rm. We will not really use that at all today. We needed that for like something that will come later. And so today, and I'll also just give you a brief overview of what I'm planning on doing in general with kind of this reading group. Is today we're going to talk about Newtonian mechanics. Now, next week, I'm hoping that we're going to talk a little bit about Lagrangian mechanics. And then next, whatever the next time is, I'm hoping we'll maybe spend actually 2 meetings, not 1, talking about Hamiltonian mechanics. And then the goal would be to kind of try and compare and contrast the 3 different formulations of classical mechanics, and then kind of compute a few examples, and compute kind of the same example in all 3 different ways, and look at what the difference is. Yes, does that make sense? That's vaguely the idea. So as of this week, you'll also start getting readings. The reading for Hamiltonian mechanics, you'll actually have like a little bit to do now. So it's more like separated, and you don't have everything to do at once. That's fine. And yeah, so that's what we are going to kind of try and follow here. Okay, so once again, I will be maybe a little bit not too rigorous here. And okay, let's start. All right, so what board do I want to use for definitions and such, if we even have any today? Okay. So in Newtonian mechanics, we will mostly consider, actually, maybe that's not the right thing to say. Okay. So whenever we think of classical mechanics, or I think of classical mechanics, usually what we're thinking of is I have some kind of point particle, and I'm trying to describe the motion of the point particle, right? And okay, maybe that's not necessarily always the case, as we see later, but that's a good place to kind of start from. Okay, so if I have a point particle and I'm trying to describe its motion, what's the kind of first thing that I probably need to define or talk about? I'm trying to describe the motion of a point particle. Okay, but that's the second step. Okay, position. So if I'm trying to describe the movement of a point particle, we need to be able to talk about position of this particle. And so to be able to talk about the position of this particle, we first need to define, where is it moving, on what kind of space. So usually, so this is kind of a maybe there's probably a definition in Arnold that is rigorous, and a good definition, but I will kind of go with my own intuitive thing of, so definition is configuration space the configuration space. This is the the possible positions that a particle could have in principle. So possible positions a particle could ever take. And so in our case, and for most of the next little while, this will always be, Rn for some n. So you might say that, and so this is strictly speaking, in terms of position, right? Not time. I'm not talking about time here. So why is it, first question that you should be asking me is like, okay, if I'm talking about a particle, why is it Rn and not R3? No. No. It's classical mechanics. No, because instead of particle, I can say particles. Do you agree? So now, so suppose I have one particle, right? So we have cases. I have one particle, right? If I have one particle, then its motion, suppose it can be defined on R3, right? Okay. Suppose I have two particles. So this means I have a coordinate for particle 1, coordinate in R3 for 1. Okay, but that means I also have a coordinate in R3, coordinate in R3 for particle 2, right? So those two coordinates together, they will live in R6, right? So then my configuration space is really not just R3, but R6, because R6 encodes kind of all the possible states. Well, not entirely, but the possible states that the system could be in terms of position. If I have two particles, where could they be, right? Yes. Let me see. Actually, I'm forgetting if the terminology configuration space includes velocities properly or not. I should actually double check that, because maybe I'm just what I'm telling you is just straight up a lie. Yes. 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 Mhm. Mhm. So this is some examples. Mhm. Okay, I don't remember. Let me double check so I'm not entirely lying to you. Configuration space in physics, let's say. The manifold, okay. The configuration manifold, okay, good. And so then, yes, okay, good. So this is just the positions and doesn't talk about velocities yet. Okay. Now, to fully specify a system, yeah. So this is kind of just a definition. Now we'll move on to a kind of assumption of classical mechanics. So one of the kind of main assumptions is that one is given the initial position, positions, and velocities in configuration space, we can, so the initial positions and velocities in configuration space determine the motion of the system. Determine the motion of my whole system. So if I tell you where every particle is and where it's going at some instant, then I should be able to then tell you where everything will be after some time t. Right? That's kind of one of the usual assumptions that you make, and we'll see why this assumption probably makes sense from the mathematical kind of perspective of this. And then the following question, after I say this, what are you going to ask me? Okay, sure, but so if yes, but the other thing you would ask me after reading the statement. No, read the statement. The initial positions and velocities in configuration space determine the motion. Exactly. How do the initial positions and velocities in configuration space actually determine the motion? Like if I told you if I told you here's some particles and here's some initial positions and their velocities, how do you actually get their motion, right? So by motion, I mean I want some kind of path in my configuration space parameterized by some time. That's what I want, right? Okay. So this motion, let me think about this. This motion is given by the solution x of t, where x of t is a function from, I don't know, some time interval, let's say some t1 to t2, into our configuration space. I don't know, let's call it Q, because that's what I just saw 5 seconds ago on Wikipedia, into Q. That satisfies what equation? Everyone knows the equation. What's the equation that we need to satisfy? There's only one equation that you could possibly know ever in first year. Guys, please. F equals ma. Yes, thank you. But we will kind of absorb m into f, and we will write x double dot is equal to some function f of x dot, and maybe t. Okay? And now this f is kind of associated with the system. So where f kind of this comes from the system, this describes the system. So what you could think of, in some sense, is maybe our classical, like a classical mechanical system, is really given by some configuration space, and this function f of x dot t, and that kind of fully determines your system in classical mechanics. Yeah. So there's a lot of caveats to what I just said, like a lot. In what sense? Well, first of all, you want, here I said, the initial positions and velocities in configuration space fully determine the motion, right? And then I tell you that the motion is determined from, this f. So if you and when you take courses on ODEs, you may know that actually, okay, in one dimensions, actually no, yeah, like this f has to be sufficiently nice and actually be properly defined on your configuration space. And if it is, then you always have at least like local solutions. But essentially, this f has to be like nice somehow. You don't want it to be too weird because then you could get issues. But okay, that's kind of a very arbitrary abstract comment that I'm making here. All right. So now let's look at, I guess, a particular case. And this would then be the kind of simplest case we can look at without actually looking at an example, is we're going to look at the example of one-dimensional motion. And then we're going to try and kind of find out a particularly nice class of forces F that will maybe let us, rewrite this problem a little bit and maybe learn something new. Okay, I'll stop for questions because what I just said is like very arbitrary and a little bit unclear maybe. Yeah? Questions? Yes, no? So I guess the main thing that I want to say is, what a configuration space is where you could be, or something that lets you define position. Okay. Mm-hmm. Okay. So right now, we will look at the following. Which are going to be systems with 1 degree of freedom. So essentially, for now, let's set our configuration space to just be equal to R, right? So the picture is that I have some real line, and I have some particle on it, and I can tell you where this particle is on the real line, okay? And I will also make this restriction that the motion is given via the function f of x. So the function only depends on your position and not your speed or velocity, right? So the question about velocity, for now, think of velocity as just kind of you take the time derivative of our path x. There will be caveats to this later, which are kind of related to what I talked about before, where we kind of will need the Jacobian, where you realize that actually, if I had some curved space, right, a velocity on top of a sphere can go these directions, but a velocity on the side of the sphere can go these directions. And you can't really compare the velocity here. You kind of have to define velocity separately at every single point. And but that's something for later. That's something we will not worry about now. For now, we live in Rn, in fact, in this case, over R, and everything works out very nicely. Okay. So the first thing I will do is, so let's define energy for one-dimensional systems. We'll start with defining kinetic energy. Energy is T equals to what? Yes. In our case, once again, we're kind of absorbing m into f, so we're kind of setting m equals to 1, or really we're just kind of rescaling everything to rescaling the force to have m included into it. So in our case, this will just be 1/2 x dot squared. Okay? Pretty straightforward. And okay, people I'm hoping realize that when I say x dot, I really mean d dt of x. Okay, like this. Okay, and if I do double dot, then I take another derivative, right? The number of dots is how many derivatives they take. Okay. Kinetic energy is this. Very good. So now if we define kinetic energy, let's define, what should I define next? Potential energy. Okay, great. Potential energy. Okay, what is potential energy? Yeah, but maybe for a specific f, yes. But not entirely. It's an integral of some sort. Yes, of what? Okay, so this is the integral from some reference point, which doesn't matter, to, so the potential energy of x to x of f of x dx. Do you agree? Why does this make sense? Yes. I said that we're restricting our attention to where the force is just a function of x. Now, you may recall that, in from your classical mechanics courses, that you wanted to define work as kind of you multiply the component of force that's in the direction of your motion, right? So if you're, say, moving this way, but then your force is if your force is pushing you this way while you're going this way, then you want to kind of project this like this and compute the integral of this kind of dot this, right? You remember something like this? So you wanted to do like f dot dx, so f, the magnitude of f times dx times cos theta, where theta is the kind of the angle between f and where your path is going, right? In our case, remember, we're in one dimension, so the force is always pointing in the direction you're going because you're in one dimension. And we will talk about defining a potential in more than one dimension, because potential in more than one dimension may be a little bit trickier than you might expect it to be. Okay, and we will discuss this in a bit. But for now, let's just keep going with it. Okay, I defined kinetic energy, I defined potential energy. The next thing I want to define is total energy. Exciting. So definition, total energy. Is E. Exciting. E is what? Come on. T plus U. Okay, good. Like this is the part that's supposed to be really quick, because this is like just more or less review. So okay, I write down the total energy and I immediately tell you that there's a theorem. What's the theorem? Yes. So total energy is conserved. Okay, what does this mean? This means that if I was to take ddt of E, I get 0. Okay, proof. Proof by simple computation, right? So let's do ddt of E. Okay, this is ddt of what? This is ddt of T plus U. T is what? Okay, 1/2 x dot squared plus the integral from x to x naught, from x naught to x, sorry, x naught to x, of f of x dx. Oh, this is a lie. There should be a minus on the u. No one caught this. There has to be a minus on the u. Why does there have to be a minus on the u? This is this. I always am like, oh, I should discuss this, and then I always forget to write the minus and don't discuss it at all. So u of x is equal to minus the integral f of x dx. Why do we want a minus on there? I guess, sure, true, fair. The theorem's true, but in like intuitively, why do I want a minus sign? So the way you like always draw all of these like potential diagrams, right? You have like some potential well, and the point is that it should be in some sense difficult to get out of the potential well if you don't have enough energy, right? That's kind of the usual intuition. So if I have a minus sign, so suppose I go along some path in some direction, right? And then it turns out that this quantity f of x dx is positive, right? As I go in some direction, right? If I go in some direction and I get that this quantity is positive, this means that the force is kind of pushing me in this direction. Do you agree? Right? So if I'm here and I'm going this way and I'm integrating this quantity f of x dx, this means as I'm going this way, the force is always positive in this direction, and that means, well, the force is pushing me in that direction. Yes? Does that make sense? I look confused. Okay. And if my force is pushing me in that direction, that means it should be very easy to go there, right? Because I'm literally being pushed there, right? So this means I want that to be kind of negative, because negative means I need, kind of less effort to go there. But then suppose F was negative, right? So that means the force was pushing against me going in this direction. Do you agree? Well, then that means that it should be difficult to go there, right? That means U is positive, right? So this means you want kind of U is higher for regions that require more effort to get to, right? Because I have this kind of force that's defined everywhere, right? At every point I have a force that's, if I was to be put there, I'd be pushed according to this force, right? And I want the inaccessible, like places hard to reach, to have a high potential, and places that are easy to get to have low potential, in some sense, intuitively, right? So that's why we need this minus sign. Also, we need the minus sign for the theorem to be true. That is correct. Okay. So, okay. Let's prove said theorem. We take the derivative, and hopefully I didn't like mess up anywhere previously in the definitions, because that would be embarrassing. So I'd have what from here? I take, what would I get for the derivative of this? Yes. It's, well, no, not quite. I'd have x dot times x double dot, right? Because this is, x dot squared, right? So I do chain rule. Yes, I first do 2x dot and then multiply by the derivative of the thing inside and get x double dot. Yes? Okay. Now, this derivative may be a little bit more tricky, because this is kind of, I also define this very poorly. So this should be some kind of dummy variable for the integral. Do you agree? So u of x is a function of where you are rather than, not in here, right? So u of x, the potential is you have some reference point x naught, and then you have some point x, and your potential at this point is kind of the integral over this region. Okay? So this is kind of where the derivative comes in. Okay. And so how do we take this derivative? We also want to use chain rule. Right? Okay. So now, if x didn't depend on time, right? What would be just the derivative of this thing dx? So these are also primed. These are dummy variables for the integral. What would be the derivative of this by dx? No, because this depends on this. I'm saying take d dx of this quantity. Yes. It would just be f of x. Yes, minus f of x. Okay, but now x does depend on t, so we have to, by chain rule, multiply by the derivative of x by t. So times x dot. This is a single dot. Okay, do people see how I went from this step to this step? In general, small aside, do people understand why the fundamental theorem of calculus is true? Yes? Like geometrically, why is it true? No. Okay. I'll quickly draw a picture. Right, so suppose I have something like this. And suppose, so I define the integral from this point to this point, right? So the integral is this area under the curve, right? So the integral is this area. And so then I'm going to ask you the question of, what is d dx of the integral up to x naught of ft dt from, some reference point to x, right? So I'm saying if I was to shift x a little bit, what this is saying is if I was to shift x a little bit, by how much does the area change, right? Do you agree? So this would be kind of the dx, and then this would be, okay, the point x, right? And so if I change this by dx by a little bit, right? Then this new addition of area is essentially this rectangle, right? But what is this? What is the area of this rectangle? Approximately f of x times dx, or yeah, dt. You're right. Dt doesn't matter. Dt. So the area of this rectangle is f of x times dt. Okay, but okay, as I make, so this is approximately that. Okay, but if this is a nice enough function, and if I take the limit kind of as dt goes to 0, you see that the kind of infinitesimal change is really just f of x. Right? So the fundamental theorem of calculus is really this picture. The fact that if you shift a little bit on the x-axis, then the amount of area you're getting is approximately this rectangle, because you're hoping that the function is nice enough and doesn't change too much if you go just a little bit away. And really, that's kind of in a sense like, oh, if this function is continuous, and we know continuous functions are integrable, then this works. Now, of course, there's functions, you could have like some discontinuities, and that would still be fine. And so continuous functions are not all the integrable functions, but this is kind of one way to think about this. Actually, yeah, you probably want your function to be continuous at that point for it to be differentiable. That sounds about right. Okay. But okay, hopefully this is a picture that people have seen when looking at the fundamental theorem of calculus and proving it. Yes. Okay. You guys are just sitting here staring at me, so I don't know if what I'm saying is like completely obvious or like very, very difficult. Okay. This is on the video. Okay, now going back to proving our theorem. We're at this step. What is there left to do? We want to show that this is 0. Exactly. So now we use the equations of motion. We're saying that, total energy is conserved. But I didn't say what I mean by this. I mean that if the particle was to undergo the motion given by the equations of motion, given by the equations of motion there, then energy would be conserved for this particle. So this quantity, t plus u, is conserved along this path that the particle undertakes. Okay. Okay, and so really, all I do is substitute x double dot to be f of x. Okay, and I get 0. So total energy is conserved. Very, very good. Yes. All right. So let's see. Is there anything else that I'm necessarily missing? Yes, there is. So one thing to notice. Okay, I guess this is not something we can notice quite yet. Okay, but okay, we've shown that total energy is conserved in this case. I'll now do a kind of little detour because Arnold, it's not a little detour, it's an important detour. But I will kind of make this statement that I won't go too much into detail about, but it'll probably appear as some suggested exercise, which is phase space. So phase space. And let's look at the motivation for this. So what do we have? We have x double dot is equal to f of x. Do you agree? Okay. So this is a second order differential equation, right? We want to find a function x of t such that it satisfies this equation, right? This is what is known as a differential equation. Have you guys seen? Oh, this is not showing anything at all of any use. Okay. Have you guys seen what a differential equation is before? Yes, hopefully. Okay. Now, the thing is, this is a second order differential equation. Okay. Let's see if we can reduce this to be a first order differential equation. And in fact, we can. So, in fact, this is completely equivalent to the following system where I do x dot is equal to, not x dot, so y dot is equal to f of x, and y is equal to x dot. Is this correct? Yes, this is correct. Okay. All I did was I just said, let's call the derivative of x with time. Just let's call it something else. Let's call it some other function, and say that this is equal to y. Right? And then, okay, if y is equal to x dot, then y double dot is equal to f of x. Okay? Yes? Now, the question is, what is kind of different between this picture and this picture? Well, we've kind of introduced a new kind of degree of freedom. We introduced this new function y, right? And so now we're searching for a function y and a function x that satisfy these two constraints. But now everywhere I only have, first derivatives of all of this, right? So I'm now searching for two functions x and y. Right? That satisfy this system of equations, and as you can see, this should be completely equivalent to this, right? Because if y is equal to x dot, then x double dot is equal to f of x, right? If there exists a function that satisfies this, then of course there exists a function that satisfies this, and vice versa. But why is this kind of useful? Well, there's many reasons. One of these reasons is that we can draw these things called phase plots. Meaning that, okay, suppose we have these, suppose we find the solution to the equations of motion. Then, instead of, one thing I could do is I could plot the trajectory of my particle over time, right? So, or this trajectory, or I could plot the position in the one-dimensional case, which is maybe easier. So suppose I had a one-dimensional case, then I can plot time, and I can plot x of t here. Okay, and my particle has this position, this position over time. So say it kind of like starts here. Okay, then it goes to here, then goes back a little bit, then it goes back to here, then it goes back a bunch, and so on and so forth. I can maybe draw this kind of plot. Do you agree? Okay. Alternatively, I could make, this fairly poor diagram that I drew here, which is just the trajectory of it. So in R2, if you had a particle moving in R2, your trajectory, okay, would look something nicer, like, something like this. I don't know. My particle started here, went this way, and ended up here, right? The problem with, say, a trajectory plot is if I just show you the trajectory of the particle, then the trajectory of the particle doesn't really tell you anything about the speed at which the particle moved along this trajectory, right? Because what could I do? Think of it as a car going along some road, right? If my car is going along this road, then what the car could have done maybe is spend 1 hour to travel this section and then travel the rest in like 5 seconds. Or it could have been going at an even speed this entire time, right? This diagram doesn't give you any of this information, right? And neither does this diagram. Okay, this diagram does. Do you agree? But then maybe it would be more difficult to draw this kind of plot if you had more, more dimensions or something. Regardless, we can also draw a third kind of diagram, which is a phase plot, which is when I take and plot the velocity of my particle at every point in space. Right? So if yes, and in fact, let's look at this very briefly, right? Actually, sorry, I should be writing this differently. I should be writing this, sorry, x dot is equal to y. I'm so sorry. So now this is kind of more manifestly clear. Yes. So now let's see what we should be kind of plotting here and how this relates to this system of equations, right? So now, instead of looking for for two functions, right? I'm looking for I'm looking for what? Sorry, instead of looking for one function, I'm looking for two functions, right? X and y. And I'm saying that let's plot these functions x and y, because y is the y-axis, x is the x-axis. By the way I named them, this is probably the thing that I should be plotting. And let's see why this is the thing that I should be plotting. Okay, so if I had some coordinate x of t and y of t, right? So I want to maybe plot this kind of path, right? That makes sense. This makes sense as a path. This is the path that I will have to plot, right? But let's see what, like if these equations can tell me something directly about the path. And what can they tell me about this path? They can tell me that if I was to take the derivative of this d dt, right, then this derivative will be what? This derivative will be y, comma f of x. Do you agree? Yes? So now, what is this? This is some vector, right? So this is some curve in my xy space, right? And this is a tangent vector to this curve. Do you agree? Okay. So, suppose my motion was given by, I don't know, something like this. This was my x of t, y of t. This is some trajectory in phase space. I know that all of the, kind of at every point here, the vector tangent to my curve has to be y comma f of x. Do you agree? So now, what could I do? Suppose, instead of kind of directly trying to figure out what the trajectory in phase space is, right? Because that might be difficult. To figure out what the trajectory in phase space is, I need to solve this differential equation, which is equivalent to solving this differential equation, and that just might be hard to do, right? I just might not be able to do it immediately, right? So instead, what I could do in my phase space, x dot x. So instead, y and f of x, well, this is given to me. I already know what f of x is, and well, I know y because I can just choose a y at every point. Do you agree? So instead, what I could do is I can try and plot this vector field on here. So at every point, I will draw a little vector arrow pointing in some direction. So I can draw a, kind of whatever it may be. I don't know. Maybe my vector field is something like this. Okay, and I'll have like an arrow at every point, and then I'll draw these arrows. But okay, now I can always draw the vector field, right? If I can just draw it, if I draw it at enough points or whatnot, right? I can always draw a bunch of little arrows given a function for them. Yes, at every point. And so if I do this, what can I do? I can then kind of try and figure out what these curves will look like based on the vector field. Why? Because I know that the curve has to be, the curve in phase space has to be tangent to all of these arrows. Do you agree? And so then, if I knew that these are the arrows, then I can guess that the curve would be, something that goes like this. Do you agree? So this is kind of why this is useful, is just kind of looking at rewriting this equation like this and kind of plotting this vector field in phase space. I am able to deduce something about the behavior of how all of these functions look like. So how this trajectory looks like. And so I guess usually people don't write y. Usually people just directly write x dot, and they kind of plot things in the x and x dot coordinates, right? So you're kind of telling me what is my speed at every point x. And so this is, I guess, a little bit of a deviation, but what's a really common example that everybody knows and looks at? Example of a function f that gives you an interesting phase portrait, which I have just failed to draw. Close. F of x equals minus x. So why is f of x equals minus x such a nice example? Why is f of x equals minus x such a nice example? What is this? Physics people have to know. Please. This is very, very easy. What is f of x equals minus x? Please. What is this? What? Yeah, yes, there we go. It's a mass on a spring. Yes. This is the usual example for a harmonic oscillator. Please tell me that all of you know what this is. Yes, you've seen this before? So what does this look like in, don't worry, we'll talk about, this is an example that we'll kind of talk about later in actual detail. But okay, so since you have missed this, what was the point of rewriting these equations like this, right? So y dot is equal to f of x, x dot is equal to y. Because then, suppose I wanted to look at x of t, y of t. That's some path in some space, right? X of t, y of t. If I was... Okay, good. That's fine. So now let's look at this example. If f of x equals to minus x, then... oh, wrong camera. Then what are these vector fields? The vector fields are x... so are y comma... Oh, sorry. Wait. Yes, the vector fields are then y minus x, right? And let's look at what these vector fields are, right? So what you can notice fairly quickly is that y minus x, this vector field, this is some vector field at the point xy. Do you agree? This is what the vector field is at point xy. You can notice quite easily, though, that this vector has to be orthogonal to the radius vector xy. So y minus x is orthogonal to xy. Why? Because I just take the dot product and get that it's 0. So I know it's perpendicular, right? X times y minus x times y is 0. Yes? If I take the dot product of these two, it's 0. So if I wanted to kind of look at this point xy, right? If I was to plot y minus x, I know it's going to be somehow perpendicular to this radius vector. Do you agree? Okay, and what else is there? And now I just need to, you can also notice that the magnitude of this vector is equal to the magnitude of this vector, right? Well, because it's the same coordinates, right? X squared plus y squared is the same thing as y squared plus minus x all squared. Yes? So in this case, we just need to figure out which direction we're going to be pointing in. So if I am at, in this quadrant, right, y is positive, minus x is negative. So this means I'll be pointing this way, right? Okay, and so I know that if I was to draw a circle, that's a really poor circle. Let me retry. That's an even worse circle, but that's fine. You know, these trajectories, sorry, these not trajectories, this vector field will just be kind of these tangent lines to some kind of circle. Okay. Right? And all of these have the same kind of magnitude on this circle. Okay. And so, okay, there'd be more arrows out here that would be bigger, but they would also be kind of tangent to some kind of circle. And if all of these are tangent to some kind, right, so if I didn't have the circle, and if I started here and tried to kind of flow along these arrows, right, then you can kind of expect that my trajectory will end up being the circle, right, because, well, all of these arrows are tangent to the circle to begin with. So just kind of from looking at this phase diagram, you can quite literally already guess what the trajectories in phase space will look like. Right? And the other thing that you can guess is that actually, since my trajectory in phase space, if you look at these arrows, all of these arrows have the same magnitude at every point on my circle. Do you agree? If they all have the same magnitude at every point on my circle, this means that I should be moving along the circle at a constant speed. Do you agree? Okay. In that case, you can then more or less guess that up to some initial conditions and some phase, my y has to equal to sine omega t, and then my x has to equal to cos omega t, and maybe I'll have like some delta phase shift here. Right, just from looking at this diagram, just from plotting these vector fields and studying them, we have managed to guess, we've managed to essentially guess what the solution to the harmonic oscillator should be, right? It should be y is sine, x is cos, or maybe I want a no, that's fine. Oh, true. Right. Omega is 1 because I set omega to be 1 by doing f of x equals minus x. Right? Because this is like this has a root k over m in it. And and omega is root k over m, and I set this to be equal to 1. Right. Yes. In principle, yes. But since I wrote this delta, that means I can say phase shift by something that I want and make it work out. So yes, but maybe not. Yeah. Okay. Actually, no, then I guess there would be, you're right, let's add a phase shift here too, or something like that. But okay, essentially I know, sorry, there has to be a phase shift on both of them so it stays on the circle. You're right, yes. But, so maybe I do need a minus sign here. Do I? Yes, but essentially just from looking at this, we've managed to more or less guess what the solutions have to look like, right? Just because of the fact that the vector fields kind of always are perpendicular to my radius vector. So I know if I'm ever moving, I have to be moving perpendicular to where I'm current to the radius vector. And I know that all of these have the same length, so I kind of know I have to be moving at a constant speed around a circle, just from looking at these vector fields. Okay, this may have been unclear, but this is why phase portraits are important. You can guess behavior of things from there. And I think a common question that, at least is in this book and in general, is you're given some arbitrary potential, and you're told draw a phase portrait and figure out what the behavior is of the system from that. And so I think that will be an exercise for you guys to think about this. Okay. It's 12:23. Okay, so we've gone 1 hour. Do we want a break before we talk about the three-dimensional case, or do we want to just continue? Okay, let's do a 3-minute break, and I'll... okay, so we'll start again. So let's do a quick recap, right? So we defined the configuration space, we defined the motion, right? How we get the motion on this configuration space to some system. There's an associated function f of x. And okay, we showed that in the one-dimensional case, we can define the kinetic energy and we can define the potential energy. We get the total energy. And if my force only depends on my position and doesn't depend on time, then we get that the force is, the total energy is conserved. Okay, that's good. So now, let's try and do this in n dimensions. Okay, and let's kind of follow the process and try and maybe prove the same theorem, but then we're going to run into issues and then spend the rest of the hour trying to solve these issues. So, okay, suppose now my configuration space Q is, so for now, let's still consider the motion of a single particle. So now Q is R3, okay? Or maybe R2 could be R2. Just anything that's not one dimension. Okay, and I have one particle. So the kind of the position of the particle is given as some function from some time interval to R3 or R2. Good. So let's define the kinetic energy. So define the kinetic energy. What should the kinetic energy be? Yes, exactly. So one thing that we know on R2 and on R3, we have the usual inner product, right? So these are actually inner product spaces. Inner product spaces with some kind of inner product structure on them. Do you agree? And like usual, we define x dot to be d dt of x, right? X of t. So what I mean by this is I have d dt of the first component, x1 of t, and then d dt of the second component, and so on and so forth. Okay, however many components there are. And what I can do is I can define the kinetic energy T to be 1/2 times the dot product, or the inner product, of x dot with itself. Why is this possible? Because in this case, once we take x dot, the derivative of x, we can still think of it as some vector in R3. Okay, but maybe this is not exactly the right way to think about it, and we will think about that later. But for now, since it's still a vector in R3 and we have this inner product over R3, then I can write this down. Okay? And by inner product, I write inner product brackets, but I just mean the usual dot product right now. I'm just using the inner product so that when we generalize all of this, it will be a lot easier. Okay? This makes sense, yes? Very, very easy. So now, I didn't say anything about the force. So let's assume the force also only depends on position. That f is a function from Q to R to R2 or R3. Okay. So it doesn't depend on the speeds at all. Okay. So then let's define potential energy. How do I define potential energy? Same as before. Okay, so it should be, what should it be? U of x should be exactly. So what we want to do, like before, we want to try and define our potential energy as minus the integral of the force somehow, right? But then we run into this issue that in R, if you wanted to go from x naught to x, there was really only one way to get there in terms of space, right? You just have to, traverse the space between x naught and x, and then you can always define an integral like that. In the cool part about R is, okay, if my path that I chose was to get from here to here, if instead of going directly from here to here, I first went here and then went back here, right? Then this contribution to the integral actually cancels out, right? Because I'm going there and then I'm going back. right? This gives a negative contribution, this gives a positive contribution, and they just cancel out, right? So the only thing that really matters is this distance between x and x naught. Okay. Now suppose my configuration space was Q equal to R2. Okay. Now suppose I want to define, the potential at this point with reference to this point, right? Now if I want to define this integral, I need to define some kind of path to take this integral along. Do you agree? And so this question is, okay, well, what if I chose this path versus what if I chose this path? Do you agree? What if the integral along this path and along this path is not the same, right? Then what happens? Then I can't define a potential. It's as simple as that. So now we run into this issue that, okay, you have a restriction. So to be able to even talk about potential energy, you need to look at a very particular kind of F. You can't look at all F. So need to define so need to figure out what F I can, to figure out what F I can use that have a well-defined potential. But what is the first thing that I need to do even before that we still haven't really talked about? So what was the potential before? An integral, right? Over a path in Q, in R. But now we have this, we're taking an integral over a path in some higher dimensional space. We haven't defined what that is yet. Do you agree? Yes? So, and this is where kind of differential forms start to slightly appear in a very vague sense. You don't need differential forms to make it appear, to define this, but I will first define it without differential forms and then tell you how this is defined, how you could use differential forms to define this. Okay, so I have some function, I have F, which is a vector, right? It's a vector field. F now is a vector field because at every point I have some kind of vector in R3. Do you agree? And I want to compute some kind of integral that turns into a scalar, right? I take an integral and I get a number. The integral is a number, not a vector anymore. And before, kind of in classical mechanics, which you've learned that a little change in so U is given kind of as the what did I write before? I wrote F times dx times cos theta, right? Do you agree? So this was if I'm going along, if I have some path, right? Then what I do is I'm at some point on the path. I look at where am I going? If I'm going this direction, right? What's the direction that I'm going in? I look at kind of the tangent vector to my path, and then take the look at which component of the force is kind of going in the same direction as my path. Do you agree? And yeah, I do that, and then I take the dot product of them, right? So now let's try and rewrite more carefully what this is. Okay, they write it like that. Is this Sorry, let me think about this. Yes. So suppose this is my path is gamma of t, right? And this point is gamma of t naught, right? At some, or I don't know, some particular ti. Let's say, do you agree? Then, okay, the magnitude of f dot cos times dx, okay, all of this is going to be really equal to my force f at gamma of t, right? So my force at kind of this point. This force could really be pointing anywhere, I don't know, right? And I want to take this force, take the absolute value of this force, and kind of multiply it by the angle between where the force is pointing and where I'm going, and multiply it by a small change in my, in my path. Do you agree? Is this right? Yes, I think this is right. Let me see. Mm-hmm. Mm-hmm. Okay. So I just want to double check that I'm not forgetting a completely obvious thing. And I remember that there's an example which talks about this in a later in the book, and I just really am afraid of making a mistake and not commenting about it. Come on. This is just not talk about it. I literally saw this, looked at this yesterday. Why do I not remember it already? Okay, that's fine. If I don't find it, I don't find it. Mm-hmm. Yeah. Yeah. Okay. So now, how do we integrate this, right? Well, what we want to do is we want to take this path, kind of split it up into some even, bits. Take this up and add all of this up, right? In the usual way. Is this kind of making sense? So what I want to write down is I want to kind of do this sum. F gamma of t dot cos theta d gamma of t. Okay. However, you can notice that, well, d gamma of t, sorry, there should be an absolute value around d gamma of t. D gamma of t is itself a vector. Do you agree, right? It's the kind of the tangent vector to this curve. Do you agree? So what this whole quantity should be, this is really just the inner product between my force and d gamma of t. Do you agree? So this should really be, so how work should be defined is really through this integral of f d gamma of t along some path where what I do is I take this path, I break it up into bits, look at kind of the tangent piece at each point, and compute this like that. Do you agree? However, what you may notice is actually d gamma of t, you can expect that d gamma of t really should be, so d gamma of t really should be gamma dot of t dt. Do you agree? Like if I move t a little bit, my gamma should change by gamma dot of t. Right? So then I should be able to rewrite this integral in terms of this path if I really wanted to. So this then could be an integral over t of f times gamma dot. F dot gamma dot. Okay. And notice that this is indeed reparametrization invariant, right? So if I decided to go along this path faster or slower, gamma dot, so dt. If I decided to go along this path slower or faster, then just by change of variables, you can check that. As long as the actual trajectory of the path is the same, then this integral is the same, right? I don't know, did that statement make sense? Right? If I took the same path, right, and instead of just going and went at constant speed versus if I went the first half of the path really quickly and the second half really slowly, this integral will still be the same as long as I parameterize this correctly. Okay, so now this is kind of, well, this is something that we know how to do because now this is an integral over just given a path. This is just an integral over some time t, right? This is really just you have a function defined on t, and then you're integrating that, and we know how to do this integral. Do you agree? So now, okay, now we have a good sense of what this integral should be and how to define it. So I will now make a short aside. So can I erase this because this is fairly straightforward? Even though this is kind of what we're trying to mimic, maybe I won't erase this. Maybe I will have to. Yeah, I can definitely erase this actually, because this board is not well used. So, what's the connection of this to differential forms, and how does this relate to whatever it is we want to relate this to? So we just said that, okay, we could, well, not this. We could define this kind of mysterious integral f dot f d gamma, and this is over gamma, equal to t f gamma dot of t dt, right? And so, quick question. So before, remember I was writing f, yeah. So how did the dt get outside of this, outside of the inner product, right? Well, if I make the argument that d gamma of t is equal to gamma dot dt. Remember, gamma dot is a vector, dt is a scalar, and inner products are inner products. You can factor out scalars from them, right? So this is kind of why you can do this intuitively, maybe. So then the question is, how does this? What is any of this? Well, it turns out that I can define a one form. Do people remember what a one form is? Do people remember what a linear functional is? A linear functional, so you have a vector space and it takes in a vector, outputs a number, right? A one forms are alternating, or so a k form is an alternating multilinear function with k inputs. So you can plug in k vectors into it, and it's linear in each of the entries. And also it has the thing that if you swap any two inputs, you get a minus sign on the output. But in the case if you have only one input, then this whole thing about switching two inputs doesn't make sense because you have only one input, right? So you don't worry about that part of what a k form is too much. So you can think of it as a linear functional. And so if you give me a force F equal to F1, F2, F3 of X, right? Then I can define the following thing. I can define this W, or maybe this, let's call it omega. I can define this form equal to F1 of X dx plus F2 of X dy plus F3 of X dz, which is what? So what are these dx, dy, dz? In this case, this is just notation. So this is just the linear functional So maybe I should do dx1, dx2, dx3 for consistency. This is just a linear functional that sends, so dx1 of 1, 0, 0 gives me 1, and dxi of 0, 1, 0 gives me, dx1 of 0, 1, 0 gives me 0, dx1 of 0, 0, 1 gives me 0. Okay, so I just define dx1 to be the linear functional that sends e1 to 1 and all the other basis vectors to 0. Right? So just don't think about this as anything, just think about these as just linear functionals. So it takes in a vector, it's a linear function that takes in a vector as an input, outputs a number. And dxi is something that really, I can summarize this as dxi applied to ej is the Kronecker delta ij. So it's 1 if I is equal to j and then 0 otherwise. Right, so this is a linear functional. Do you agree? Sorry, yeah, this is a linear functional. Yes? Do you see this thing that I've defined? Pardon? No. Why? Because the force is a vector at every point. This is a linear functional. A vector is a vector. Do you agree? A linear functional is a function that takes in vectors and inputs as inputs and gives out a number. They are not the same thing, because one is an element of the vector space, the other is a function. Yes? Now note that this linear functional is not constant in space. So it's kind of, this defines a linear functional at every point in space, a different linear functional at every point in space, because my force depends on space. Do you agree? So you're right, this is a really key distinction. This is not the same as F, because they're different kinds of objects. And on flat space, it looks like they're the same. But if you had like curved space, then you will realize very quickly that these are completely like very different things. But, okay. So you believe that I can define this kind of functional. Do you agree? And this functional is defined on all of space. Do you agree? But then, what is our case? In our case, we have all of space, and we have a path on all of space gamma of t, right? And what we have is we have our, this gamma is defined on some interval, say 0 to t, and this gets mapped into gamma of t, right? And so we aren't interested in this linear functional on all of R3. We're interested in this linear functional just on gamma, right? So we kind of have to, what do we have to do? We have to take this linear functional and somehow restrict it to only be taking stuff related to gamma. Do you agree? Yes? Because look, right now, what this linear functional does, it's defined on all of R3, so at every point, I have some linear functional defined. At every point, I have a linear functional, and this linear functional can take as input this vector, this vector, this vector, and so on and so forth. It can take any vector as input on all of R2 or R3. I'm drawing a picture in R2. But here, I'm drawing a curve. And this curve doesn't have tangent vectors in all directions. It only has tangent vectors in really one direction, right? So this linear, we need to redefine this linear functional, so as input, it only takes tangent vectors as kind of this tangent direction, just specifically for this curve. Do you agree? So this is called the pullback of gamma, of omega under gamma. And, well, so this is the pullback of omega under gamma. And so what we want to do is, instead of plugging in some vector tangent to R2 or R3, we want to use this kind of K-form that is defined on all of R3, and somehow restrict it so that instead of it being a K-form on R3, this is now a K-form on our path, or even nicer, a K-form on our kind of interval instead. And how do we do this? Well, we do this in the obvious way. Because we're like, okay, well, what's dx1? Well, whenever if I have a tangent vector, I'm only allowed to have tangent vectors here, right? That are tangent to my curve, right? So I'm only allowed to have stuff that's like parallel to gamma dot, right? So dx1, I'm just essentially going to now plug in whatever component of my tangent vector is into dx1 and just use that. Okay, but if I plug in gamma dot of into dx1, I'm just going to get kind of d gamma 1 of t, and so that's just going to be gamma dot dt. So I'm not explaining this well at all, and I will move on from this very quickly, so that you guys actually get to read about this properly. But if I was to V, this is what? Okay, this is just going to be the gamma dot 1 dt applied to V. So why is this the case? Yeah, why is this the case? What am I doing? Well, suppose I have a tangent vector kind of here. Do you agree? Right, a tangent vector here. D gamma, right, what I can do is I can take this tangent vector here, map it to a tangent vector here, right? And then plug it into this linear functional. Do you agree? I can take a tangent at this point t, I can map this tangent vector to a point gamma of t, and then plug it into this linear functional at this point. Do you agree? Right, so at this point, I have a linear functional defined, omega of at gamma of t, right? So this is a function that takes in a vector in R3 and sends it to R2, right? But I want to define a differential form on this interval, right? So I want to define a linear functional at every point on this interval. But the only kind of tangent vectors here are one-dimensional. So I want to take, if I want to define this here, I want to take this vector, kind of embed it into this three-dimensional thing, send it here, and then apply it to the differential form. Do you agree? And this is how I get from this equation to this equation. What the pullback is so the differential, so this differential form, right? It's a linear functional at every point. It can take in some vectors and outputs a number, right? And if I want to restrict it kind of to this curve, I want to only be plugging in tangent vectors of this. So what I want to do is if I have a tangent vector v here, so so if this is v, my tangent vector on this space, right? And I have a differential form that is kind of defined at it's defined on R3 cross R3 to R, right? Because the differential form is at every point I have a linear functional, right? So at every point in R3, I have a linear functional. So this is the point where we are in R3, and this is the kind of vectors that it can take in. Do you agree? What I want to do, so omega at x, input it at v, right? What I want to do is I want to kind of use this differential form to define a differential form on the initial space that I was on, right? Which defines my path. So what I want to do is really define a differential form that corresponds to my path, and the easiest way to do that is of some other vector e is to take this differential form, evaluate it at gamma of t, and plug in d gamma of my vector e, like this. Right, so I have something that takes it that defines a linear functional at every single point here, right? And I want to pull it back to this line segment which defines my path. So what I do, I know that it takes in some vector at every point here. So what I should do is I should take a vector here, map it via the Jacobian to this point, and then plug it into my differential form. And that's really all I did going from this line to this line, right? All I did is I was like, okay, if I have a vector here, v here, that's tangent this way, it will get mapped to something in the following way. Like this vector v is going to be stretched, is going to get mapped by the Jacobian to gamma dot gamma 1 dot gamma 2 dot gamma 3 dot v, right? Because remember, gamma 1 dot gamma 2 dot gamma 3 is the Jacobian of gamma, right? Because gamma is a function from R to R3. I can write down a Jacobian for it, and I'll get some vector. Okay, this is maybe very unclear. What is dt? dt is a linear functional. Yes. Yeah. So what is dt? No, No, I said forget. This is notation for linear functionals. So a linear functional is something that takes in vectors as an input and gives a number as an output. dt is a linear functional that takes in a tangent vector here as an input and gives a number as an output. Right? So dt has to have some input, which is going to be this vector v. Right? So at every point, I can draw some tangent vectors, and this dt is one form that's defined at every point, and it takes in as input some vectors and outputs a number. Right? So before, we had this as the one form. So this would take as input at every point. This would define a linear functional that takes in tangent vectors as input and spits out a number. And what I want to do is I want to use this and kind of define some linear functional that takes in vectors as input here, tangent vectors as input here, and spits out a number using this. And what do I do is I just take whatever I have here, look at a tangent vector here, map it to be a tangent vector here, and then plug it into here. No. dt is a one form that takes in a tangent vector here and outputs a number. And there's really kind of only one kind of thing here that does that because it's one-dimensional, right? The only linear functional that does this is just some scalar multiple of the coordinate of this vector, of the tangent vectors at every point. So you can think of dt as something that gives you the length of the tangent vector at some point here. So v is some tangent vector at this point, and dt just tells me the length of v with direction, like it could be negative. So yeah, v is in R1, correct. Oh, well, I'm mixing up notation here. So let's maybe have this v and this b, I don't know, some other vector u. Okay, this is very confusing, and this is not at all the point of what I wanted to talk about today. And we'll only have 20 minutes. Anyways, this will make more sense in future sessions. I don't know, maybe I should like cut this part out from the video completely, because this doesn't make sense. That's fine. I'll have like a thing in the description being like, skip this part. Okay. We will return to this, and this will make a lot more sense. For now, I will simply erase it, because I failed to explain this clearly. That's fine. So now let's go back to, okay, what were we doing before? Sorry, let's go back to what we were doing before. Forget everything I just said. What we were doing before is we defined, is this mic still on? Good. We defined, we had a force. We defined what the kinetic energy was. That was very, very easy. Then we we're like, okay, let's try and define potential energy. Okay, we figured out how we would define the potential energy if we had some fixed path, right? And we defined this integral. So just if you're given a path gamma, it's the f inner product gamma dot dt. So over the time t that the path takes place. This integral makes sense, yes? People understand how to do this integral? This is just your usual one-dimensional integral that you've done a million times, right? Okay. Now the question is, okay, well, suppose I had two different paths, between between x naught and x. So okay, this was x naught, and then this was x, right? And I, if I want to define a potential function in a nice way using this integral, I want to make sure that if I choose this path versus if I choose this other path, then my potential energy is still the same, right? I want my potential energy to be a function of position, right? And it should tell me how hard it should be to get to Okay, and of course I'm missing a minus sign, but okay, it doesn't matter. Well, in this case, I wasn't talking about work. In this case, I was talking about, in general, how to define this whole potential energy business. Doesn't matter. The point being that, okay, we want to make sure that this potential energy is defined as a specific point, and so we wanted this definition of potential energy by saying we integrate, this thing along some path. We want this to be independent of the choice of path, right? So immediately this tells me that not all, in fact, not all functions, not all vector fields f have this property, that if you were to take this integral along some path, this integral will only depend on the endpoints. Do you agree? So we will now define the notion of a conservative force. And the notion of a conservative force is, it's essentially all the forces where you can, in fact, define a potential energy in this nice way. And we will kind of restrict our attention to conservative forces. So definition. A vector field F from, say, R, doesn't matter, even Rn to, from Rn to, I guess it's Rn, right? Or, well, no, let's stick to R3. So, right, we're talking about one particle. So R2 to R3 is conservative. So if this integral over gamma of f kind of d gamma, which we managed to define by doing this, I don't know, from 0 to some time t. So if this integral only depends on the endpoints of gamma, meaning what? I.e., gamma dot. So sorry, meaning that gamma of 0. So meaning if there exists gamma of 0, so some other gamma such that they have the same start point, and gamma 1 is equal to gamma 1 of this other one, so they have the same start point and end point, then the integral over gamma of f d gamma is equal to the integral of over this other path, okay, f d gamma over this other path, right? So we essentially define a vector field, a conservative vector fields, to be the vector fields that kind of have this property, that these integrals are the same regardless of the choice of path you take. Okay. Sometimes, at least in Russian, you call these like potential vector fields. Why? Well, because you can introduce a potential. Okay. So in fact, now this calls for some sort of theorem, right? So theorem. Theorem. So f is a potential force or a conservative force. If and only if F, so it exists a U in a U which is a function from R3 to R, such that F is equal to minus Jacobian of U, or minus grad U, because grad in this case is the same. So what is grad? Do people remember? You can't see anything again. What was the grad of a function? Yes, okay, but sure. What okay, what is the Jacobian then of this? Give me a function. Pardon? Yeah, give me an expression, explicit expression. So, okay, I differentiate with respect to what? Well, you always have a basis. It's the standard basis. Okay, so partial x1 u, partial x2 u, partial x3 u. Okay, so I just take this function and I differentiate it with respect to each of the coordinates x1, x2, x3, and this defines a vector in R3. Actually, this defines a linear functional, but I can think of this linear functional as a vector in R3. Okay. So this is the theorem, that if I can write f to be equal to this thing, then everything's fine. Then my force is conservative, and in fact, nothing depends on the path. And it turns out this is an if and only if. So if f is in fact equal to minus grad of some potential function, then the choice of path does not matter. Okay? So now, we'll prove this theorem and we will stop. There should be a minus here, yes. Because it's minus grad u, correct. Okay. So why is this kind of the obvious thing that should give us the answer? Why will this not depend? Why is the integral of minus grad u somehow not depend on the path, but other things would, maybe? Or at least, yeah, why would this definitely not depend on the path that you choose? If you integrate this over some path, why would this not depend on the path that you choose? Exactly. So the idea is we are going to somehow use the fundamental theorem of calculus in a clever way, and we will see that if you were to take this the integral of this, then none of this would really. Then it will only depend on the endpoints where you started off and ended from by the fundamental theorem of calculus somehow, right? And if you were to go kind of the other direction and say, oh, suppose that the force is conservative, how would we find u? Well, if the force is conservative, then we can define a potential energy because we said it doesn't depend on the path. So just define the potential energy using the integral and show that f is then equal to minus grad u. Okay, straightforward. Maybe. Okay, so let's prove this in kind of the maybe in one of the directions, and then we'll stop. And okay, proof. So let f equal to minus grad u. Okay. So maybe I'll write this symbol. This is the symbol for grad. Okay. So it's equal to minus all of these partials. ddx1u, ddx2u, ddx3u. Okay. And what do I want to do? So I want to show that if I had two paths that had the same start and end points, then this integral, then the following integral would not depend on the path. So gamma f t gamma should be equal to this other integral f t gamma. Okay. So I will just write this. I'll write this in 2 dimensions, but the answer will be clear the same in 3 dimensions. I just don't want to write an extra term. So here we're assuming that gamma and gamma twiddle are kind of both paths parameterized by both from 0 to t to r. You can generalize this if they had different parameterizations. Maybe I'd parameterize one from 0 to t and the other one from minus t to 5 or whatever it is. You can choose many different parameterizations. None of it matters. But for convenience, I choose this. And of course, these two paths have to have the same endpoints, right? So gamma of 0 is equal to gamma twiddle of 0, and gamma of 1 is equal to gamma tilde of 1. Okay, so these are the assumptions. So this is what I want to prove this, and everything else is the assumption. Okay, so proof. So let's rewrite this integral as an integral from 0 to t, right? So if I was to write this as an integral from 0 to t, I have what? I want to do f1 at gamma t and multiply this by gamma dot 1 plus f2 gamma of t, multiply this by gamma dot 2 plus f3 gamma of t, gamma dot 3, and all of this dt, right? Okay, where this is just gamma 3 ddt. Okay, right? Gamma 3 is the z component of my path differentiated. Gamma 2 is the y component of the path. Gamma 1 is the x coordinate of the path. Okay, but now we assume that f is equal to minus grad u, so I can kind of substitute it. I can substitute this into here, right? So this is the integral of what? This is the integral of d x1. Well, I'll just write this as a sum. The sum of du dxi evaluated at gamma of t dot gamma dot I of t dt. Do you agree? There is a minus, of course. There is a minus. Do people see that I didn't do anything yet? I just wrote down this integral, and I plugged in the fact that f is equal to minus grad u into here. Yes? Didn't do anything fancy. So now I can split up this, integrate each term separately, right? Yes? People believe me? I can integrate each term separately? Okay. So I can swap these guys. Okay, but what does this... Am I doing this correctly? Maybe. What does this really look like? Right? This is di u dxi times gamma I dot t. And this is evaluated at gamma dot. What does this look like? This looks like chain rule of some sort. Yes? Yes. But then these are partial derivatives, not total derivatives. Maybe that's... maybe there's something that I need to say about this. But the idea is, okay, this looks very much like chain rule. So I can really replace this as the kind of sum of integrals. So this was from 0 to t, this was from 0 to t. I can replace this as the sum of integrals from 0 to kind of gamma I at t of the derivative of u of there we go, of this no, sorry. So this is still the integral from 0 to t of the derivative dxi of u of gamma t. Oh, sorry. What am I saying? This is the derivative of, yes, so d dt. There we go. Am I writing this correctly? No, I'm not writing this. Wait, sorry, I'm not writing this correctly. This is this derivative. Yes, correct. I am writing this correctly. There we go. No sum, because once I take the derivative of with respect to t, like I'll need to kind of differentiate in each coordinate. Sorry, I'm not being clear. So what's happening? What's happening is I have a function u that takes in a point in R3, sends it to R, right? But then before this, I have a function gamma that takes in a point in R and sends it to R3, right? So okay, if I want to compute if I want to compute the derivative from here to here, that would be the same as computing the derivative from here to here, and then the derivative from here to here, and then composing the two of them. Do you agree? And how do you do this? Here, I take gamma dot, right? And then here, I take grad of u. Do you agree? So I will be doing grad of u kind of applied to gamma dot. So at t, and this would be grad of u at gamma t. And then this should give me the derivative ddt of u of gamma t. Right? Do we see why? I took it. It's the kind of best linear approximation of the thing here. Why? Because I took the best linear approximation of gamma on R3, and then I took the best linear approximation of u on R3, and then I composed the two of them, and hopefully that intuitively that should give me the best linear approximation of gamma, of the composition of U composed with gamma. Do you agree? And so if I was to explicitly write this out in coordinates, right? What is grad of U at gamma t? Grad of U is, well, that's just du dx1, du dx2, du dx3, right? Evaluated at gamma of t. And then, right, so as you can see, this is a matrix that takes, is that visible? That takes as input stuff like vectors e1, e2, e3, right? And outputs of one-dimensional thing, right? So this is the best linear approximation of U. But first, I need to plug into it gamma dot. But gamma dot is the vector gamma 1 dot, gamma 2 dot, gamma 3 dot. Do you agree? So this is a vector. This is well, I guess this is a one-dimensional matrix. And well, not a one-dimensional. This is a matrix with 1 input, 3 outputs. And this is a matrix with 3 inputs, 1 output. Do you agree? If I was to multiply these two, it would be this times this plus this times this plus this times this. So we get that this has to be the derivative of U with respect to gamma of t. Okay. Yes? Maybe? This is just matrix multiplication. This is why we needed the Jacobian. To be able to figure out if I have a function from R to R to R, but inside it's like from R to R3 and then to R, how to compute the derivative of this function if I have something weird in between. This is one reason why we needed the Jacobian, is to be able to talk about this kind of derivative. And I didn't really talk about and this is really the chain rule. What I just wrote down, this is really the chain rule for Jacobians, right? If I take the best linear approximation here and compose it with the best linear approximation here, that should give me the overall best linear approximation. If you look at chain rule is really the exact same thing, right? You're taking the derivative, here, and then you're taking the derivative here at the point where you got mapped to, and then multiplying them together. Okay. Okay, so let's finish this calculation and maybe be done with it. Okay, well, this is d dt of this function, right? And so this sum was, the sum from the matrix multiplication here. So this goes away. Okay, but what does this have to be? If this is from 0 to t, okay, well, this just has to be u of gamma of t. U of gamma of t. And clearly this only depends on the endpoint gamma of t. Oh, sorry, u of gamma of t minus u of gamma of 0, sorry. Right? And clearly this only depends on what gamma of t is and what gamma of 0 is, rather than, oh, sorry, here I chose 1 and then here I chose t. Right? This only depends on the endpoints of where my path is and not what the path is itself in between. And we, this is really, I just found a way to use the fundamental theorem of calculus to prove this. We just needed to understand very carefully what these multi-dimensional derivatives, how they work. Maybe something. Okay. And then, so this is kind of the backwards direction of the theorem. Like, if f is equal to minus grad u, then the potential is well defined, and it doesn't matter which path we use to define the potential. Do you agree? But then we might want to do the, I probably lost a minus sign here again. I did. So there's a minus sign, there's a Oh, no. This is fine. No minus sign. I didn't lose any minus signs. That's fine. And now we would want to prove the opposite direction, that if f is a conservative force, then there exists a potential function u such that um, such that f is equal to minus grad u, and I will simply write down what we are given, and then we'll stop. And then maybe next time, or I'll have you read about the proof that the total energy is conserved in this case. And how do we do this? Okay, so now the assumptions are that this integral f d gamma is independent, so only depends on gamma 1 and gamma 0. So kind of the start point, end point. Maybe, I don't know, let's keep going with t. And so now I'll just say, well, define u of x, to be equal to this integral for some gamma such that gamma of 0 is equal to some reference point that's always the same, and gamma of t is equal to the point x that I'm plugging into u. Okay. And now I just want to show that, in fact, if I was to take the grad of this whole thing, I would get this. Actually, this might not be as immediate as I thought it would be. If I was to take the grad. Okay. Let me think about this. Yeah, this would require maybe a bit more thinking and a bit more effort. But the idea is, the grad is what? The grad is we're kind of taking a derivative in the x direction, in the y direction, in the z direction. So we'd kind of, yeah, so this is a bit more difficult because you need to, oh, right. That's fine. So what I can do, so let's do this. So let's show that d dx1 of u has to equal to minus, has to equal to f1, right? How do we do this? Well, so let's choose a particular kind of path. So suppose I have x naught here, suppose I have x here, and we want to look at the derivative in the x1 direction, right? So let's specifically choose paths that go like this, and then kind of go like straight this way, right? Then if we were to choose paths that specifically go kind of straight this way, then what's the point? Right. ddx1 uf1. I want to take the limit as kind of delta x1 goes to 0 of what? Of this integral along, so let's call this path gamma twiddle, and let's call this path gamma. Note that these paths have different endpoints. So of gamma twiddle f d gamma minus integral gamma f d gamma divided by delta x1, right? But I said let's connect. Let's choose the path gamma twiddle, which is the same as this path here, and then it just extends to this little x plus delta x1 by just some straight line, right? So then this would just be kind of the same as okay, I don't want to fully explicitly show this because I need to think about it for like a split second. The idea is that this would be the same as just taking this limit of like u of x plus dx1 minus u of x divided by delta x1. Like essentially, well, I just wrote down the definition of the derivative, but the point is that if you were to expand all of these, expand this d gamma bit into the usual dt stuff again, and plug in this specific choice of path, you will get that it is indeed just the derivative in the x direction. That you will, sorry, wait, no, this is supposed to be the opposite. This is obvious. That you will just get f1, right? That's what we wanted to show. Right. Yes. So I'm once again being very unclear, but, and there's maybe a minus sign somewhere here. But the idea of this proof is to take this path, take some reference, fix some choice of reference path, connecting x naught to x. And if we want to take the derivative of this function u, which depends on this choice of paths, to in the x1 direction, let's choose like a specific kind of very nice path that connects x to kind of the direction in which we're taking the derivative in. And so then when we take the derivative, we know exactly what choice of path we made. And remember that the choice of path doesn't affect the function by assumption, so we can make this choice. And then it will be very easy to just take this derivative explicitly. If I do that. So this is x, and then this point is x plus delta x1. Okay. And essentially, if you were to write out all of this, you would get this very nice thing. But okay, I'm being incoherent now, and maybe it's best that I stop talking. Yes. The main important bit is, well, of course the proof is important, but the statement of the theorem that okay, all conservative forces are forces that you can write that have a potential in this way. And you define this potential by taking this integral along some path. And yes. Okay. This was very long and